Hey everyone, and welcome to The Explainer. Today, we are diving deep into a super important subject in civil engineering, structural analysis. This is the science that's the very foundation behind our mightiest bridges, our tallest skyscrapers, and our most massive dams. So let's get right into it.
Have you ever just stopped and wondered how these gigantic structures, despite all the forces and all that weight, manage to stand so strong for years and years? I mean, what's the secret to them not falling down? In this explainer, that's exactly the question we're going to answer.
The secret to all these structures? It's all about having a fantastic understanding of forces. And we get that understanding from a very special branch of civil engineering, which we call, you guessed it, structural analysis.
So what exactly is structural analysis? Well, in simple terms, it's the study of how any structure reacts to the loads or forces that are applied to it. The goal is pretty straightforward, to make absolutely sure that a structure is safe, stable, and serviceable. Think of it like a full-body health checkup for a building, to make sure it never, ever fails. Okay, so before we can analyze any structure, we have to understand its anatomy, its fundamental parts. For every engineer, knowing these three key elements is non-negotiable. So let's go ahead and break down a structure into its essential components. The first element is, well, the structure itself. In engineering, a structure is basically a system of connected parts, things like beams, columns, and trusses, and their whole job is to support loads. The second element is loads. These are the forces that a structure has to fight against. This includes dead loads, which is the structure's own weight, and live loads, which are things like people or furniture. And, of course, you've also got environmental loads like wind or earthquakes.
And a third and super important element is supports. These are the connections that hold a structure firmly in its place. The supports provide reaction forces that push back against the loads, which is what keeps the whole thing stable.
Now, what's really interesting on this slide is that different supports offer different levels of resistance. As you can see, a roller support only gives one vertical reaction, while a fixed support provides three reactions: vertical, horizontal, and a moment. This concept is absolutely crucial, especially when it comes to your exams.
All right, now we get to the most fundamental classification in all of structural analysis: determinate versus indeterminate structures. This is the first big puzzle that every single structural engineer has to solve.
So what's the difference between these two?
Look, statically determinate structures can be analyzed using just the basic equilibrium equations of statics. But for statically indeterminate structures, those equations aren't enough. We need extra compatibility equations. The bottom line is this: determinate structures are easier to solve, while indeterminate structures are more complex, but they're also often much, much stronger.
And this quote just makes the seriousness of it all crystal clear. A wrong analysis can bring down a structure that was otherwise perfectly designed. That's why getting the classification and the analysis right isn't just an academic exercise. It's a matter of public safety.
So the question is, how do engineers actually solve this puzzle? What tools do they have in their toolkit? Well, let's take a look. Engineers use a systematic process and some really powerful methods, which we're about to learn about right now. This quote from the famous author R.C. Hibbeler is a golden rule. What it means is that before you can analyze real-world complexity, you have to simplify it into a solvable model. We call this process idealization. See, analysis isn't guesswork. It's a methodical procedure. As you can see here, it has 5 main steps. First, idealization, where you replace the real structure with a simple model. Second, load application, where all the forces are applied. Third and fourth are equilibrium and compatibility, where you use equations to check stability and deformation. And finally, number 5, constitutive, which is where material properties come into play. This slide beautifully shows the evolution of analysis. Engineers have a whole range of methods at their disposal. It goes from classical methods, which are for manual calculations, to energy methods, and then on to the modern matrix methods, which are the basis for today's powerful software like StatPro and ETABS. So much theory, so many methods. What does it all really mean? Now we're going to connect all this knowledge to your exams and to the real world, and understand why all of this is so incredibly important. The payoff for a correct analysis is huge.
First and foremost, it prevents structural failure, which saves lives. Beyond that, it ensures we're using materials efficiently, which saves money and resources. Ultimately, it helps us create efficient and long-lasting structures, like the trusses you see in roofs or the cables in suspension bridges.
And now for the most important part for all you students out there. If you're preparing for competitive exams like the SSCJ or GATE, you need to make sure you've mastered these topics from our explainer. The difference between determinate and indeterminate structures, the types of supports and their reactions, the concept of degree of indeterminacy, real-life applications of trusses and cables, and what compatibility conditions are, these are all high-yield topics.
So, after this explainer, the next time you see a bridge or a building, don't just see it as a structure. Ask yourself this question: is it determinate or indeterminate? Go on, apply this new knowledge, and start seeing the world through the eyes of a structural engineer.